Alright, so next here we're going to talk about solid structures, and really the idea behind this that we're going to really focus on is what's called the unit cell. And so as I talked about earlier, it's all about these spheres stacking. And what we can get is what we call a lattice structure, is the whole thing is stacked together, large chunk of it. But there's going to be kind of a smallest repeating unit, and that is the unit cell. So this piece that we can just repeat over and over again, like laying bricks to make a wall or something. That's what this would be. And so if we have something like this AB layering, what we get are, one layer of one type of atom, one layer of another, so on and so forth. And that creates a unit cell that's actually a hexagon shape. So we call it the hexagonal unit cell because, again, creative with names as ever. Maybe we have, I don't know what we call this, ABC layering. How about that? That's what it is. We got three different things. This gives us a cube shape, and then we get, corners of one type, and then we get the others kind of interspersed throughout. We're going to talk about this a little bit more. And then we have simple cubic, where it's just pieces on the corners, and body-centered cubic, where there's one in the middle. And there's also like face-centered cubic, where there's ones on the face. We're going to talk about that a little bit more in terms of like finding formulas and things like that. And don't worry too much about memorizing the names, but just understand that there's different ways that these can stack together, and it's actually a very complicated problem to have the most efficient stacking process possible. It's something that doesn't have a general solution in mathematics. If you figure it out, you get $1 million. It's one of the millennium problems. And so, yeah, how do you stack these as maximum efficiency? The other thing is, they're not always going to stack with maximum efficiency. If you look at this simple cubic unit cell, there's space in the middle that's not being used. So this is not a spatially efficient. And so what you have is different degrees of attraction and repulsion in these solid structures that can lead to, different levels of favorability and different, certain compounds, like for example, water is ice. There's multiple forms of ice. There are different structures as pressure and temperature change. You actually get different stacking structures for the solid. And so you might remember in the past we showed, phase diagrams. Well, that was actually a simplified phase diagram for water because you'd actually have multiple different solids and other lines within the solid region. You'd have ice 1, 2, 3, so on and so forth. We just give them increasing numbering system. For a while there, I think it was stuck at 8. Now they got 9, maybe 10 or 12. I lost track. But different ways that the water molecules orient around each other to form a solid. And so they're all solids, but they're different solids. They have different unit cells. They have different stacking structures. And if we look at the periodic table and just kind of look at the standard stacking of our elements, specifically our metals and also silicon over here, we see that, some of it's, different shapes. And the really the main thing I want to point out is how uncommon simple cubic is because it's not spatially efficient. So most things are trying to maximize spatial efficiency. But in the case of polonium over here, it actually goes simple cubic. So there's other factors at play that are forcing it away from stacking as efficiently as possible. But now we're going to focus on, that's right, the unit cell of sodium chloride. Your book is just setting me up for this so well, this chapter. This is great. And so here's what we're looking at. This is all the particles stacked. So our sodiums, our cations are small, our anions are large. And within this, we can draw a cube. So this is not a situation where it's going to be a hexagon. It's not layer, layer, layer. They're all interspersed with each other. So we're going to get a cube. And here's what it looks like once we cut it down to just the unit cell. All right, this is the box. So I can stack another box onto this, and they will line up. There will be a sodium in the middle here, another piece of the sodium, there will be another piece of this chloride and this sodium, and it'll be the entire other half of this chloride in the middle of the face right here. So this is this is the center of the face. And so what we can do is, if you are presented with a unit cell you can figure out the formula. This is the kind of one of the only major things you can do in this chapter that I expect from you, is to be able to get a formula from the unit cell. Now we already know this is NaCl. We know it's 1-to-1. Okay, but how can we figure that out from looking at this image? Well, every single face is a repeat all the way around. And there's going to be 6 of them because it's a cube. And then if you look, there's one sodium hidden in the middle there. Okay, that's the tricky one to see. And so here's what we do. We just count up all the stuff we see in the box. We just go, oh, what's in the box? Oh, well, it's sodiums and chlorides. All right, well, how many? Well, if it's on the middle of the face like this, that is half of a sphere. That is half of a chloride, okay? If it's on the edge like this, that's a quarter of whatever it's supposed to be. So this is a quarter of a sodium right here. And if it's on the corner, it is 1/8 of the sphere that it's supposed to be. So this is 1/8 of a chloride. And if it's in the middle, it's the whole thing. If the whole thing's in there, the whole thing's in there. So when we're working on this, when we see something on the face like this, that's a half. These are 1/8. And on the edge here is 1/4. And if something in the middle, it's all of it. So if we work on just the chlorides first, I'm going to have 6 faces at a half each. So that's going to be 3. I have 3 chlorides. So like this is half 1. When I put those two together, I can do that 3 times. So that's 3. And then I have 1/8, 2/8, 3/8, 4/8. So I have half up here. There'll be half down there. So that is 4 chlorides. Okay. And that should be everything. There's none in the middle. And then for the sodiums, this is a quarter, 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 and that's all the way around. So there's 1, there's going to be 2 on this kind of belt, and then 3 on the bottom. So there's 3, and then there's a 4th whole one in the middle. And so we have 4 chlorides, 4 sodiums. So there's 4 NAs, 4 CLs. It's an ionic compound, so it's just NaCl, just 1-to-1. So that's how we can figure out the formula for an ionic compound, or for a metallic solid that's like an alloy, which we'll talk more about in a little bit. But essentially, you just count up the pieces, and then you cut out any common denominator. So it's not Na4Cl4, right? That should feel a little weird right now. And so it's just like before. We just make it NaCl. And so that's what you do with the unit cell. And the trick with this is just remember that these corners are 1/8. These edges here are 1/4. Faces are half. And if there's a whole one in there, it can be in the middle. Sometimes they're offset. This is a pretty crowded representation. A lot of times they'll shrink the sizes of these and kind of create some gaps that you can see through. But remember too, if you can see one face, you can see them all. They all have to match up because they all have to fit together. It doesn't need to be rotated a certain way. It can be rotated any which way, and all the faces should match so that you can press them together and carry the structure out. So it's not, it's a little simpler actually than my brick example from earlier, because a brick is not a cube, it is more rectangular. So there is a correct orientation, and some brick already put it down. This would be like even blocks that you're putting together. So you literally can't mess up and have them facing the wrong way. If there is a situation where you have to have them facing a certain way, that's not a unit cell. That is not correct. That means someone messed up when they were slicing it up or something. So just keep that in mind. And I will have a practice problem for this process for sure. So I'll try to find another example. I'm going to give you an unknown compound, so you don't know the formula at all. It'll be like something that we can shift around, so there's no guarantee. Probably like a transition metal that can have multiple charges, so you don't actually know what the formula is. Alright, or a transition metal ionic compound, I should say. Alright, so next we're going to talk about the last piece of this chapter, and that's going to be the idea of polymers and alloys. And so, again, it's going to be more, stuff stacking. And it'll be similar with alloys because we'll have pieces that are different sizes, so on and so forth.